Cared enough to fire me.
All right.
I'm glad that got caught on here. All right. So let's do this old-fashioned pair deck. So thumbs up or thumbs down, okay? Hey, old-fashioned pair deck, thumbs up for A, thumbs down for B. What are you, thumbs up or thumbs down? Okay, so take a read around the room. There are some thumbs up, there are some thumbs down. There are a lot more thumbs down than up. Why do you associate the 212 with the upward force here? Well, think about if we replace that scale with a board like this, okay, and our fellow is standing on a board, what's going to happen when that elevator initially starts to go up? It's going to get squished, right? What is the squishedness of this evidence for? The smoosh-poosh interaction, okay? That's telling you that the smoosh-poosh interaction is increasing. So there's our diagram for 2. Boop. All right, so let me move this a little bit, make it more convenient to deal with. Boop. All right, this is F smoosh poosh man scale. Again, the reading comes from the scale. That's, again, kind of telling you which interaction it's measuring. This is FG man, comma Earth, and for that force to change, we'd have to have a change in its mass. Okay? Are these forces balanced or unbalanced? How unbalanced are they? 55, says Taneem. So if I take these arrows, what'd you say, lady? Going up. This is pointing up. Okay, the unbalanced of 55. So watch how this works because this is new. I'm going to draw my YMCA. I go 212 up. I come back down 157. That's not all the way back down. What goes there? Well, if I drew 55 down, that would balance this. But it's not balanced. I don't want to draw something to balance it. I want to draw something that shows how unbalanced it is. Okay? So I'm going to draw a big, fat, upward arrow with stripes. So I know that it's a little different. Okay? It doesn't follow your rules. It's going to touch its butt to another arrow's butt. Touch its head to another arrow's head. Doesn't follow your rules, man. F you, okay? This is the unbalanced force. There is no feeler dealer, man. F you, okay? It's the unbalanced force. How big is it, Taneem? It's a 55 pounds worth of FU right there, okay? So that's going to matter here in a second when we go to figure out some things. So let's talk about some things, some facts of science, okay? We need to know things like, what is this guy's mass, right? Because we want to use our new shiny equation to figure out the acceleration here. Acceleration is Fu over m. So we need to know the mass of the man. Okay, what is it? His weight is 157 pounds. Okay, and so we got to get back and forth to kilograms. I maintain a strict dietary and exercise regimen to make these numbers memorable, okay? So I am 100 kilograms of mass. So I weigh 225 pounds, okay? And that's also, it's about 1,000 newtons. So if you were paying attention the other week, you know that I'm fibbing here a little bit, but it's in that ballpark, okay? So those are kind of the numbers, plus or minus 2%. So this Haas is 157 pounds. I don't know how many kilograms. Mr. Harding is 225 pounds. That's 100 kilograms. Do some math, friends. What does this end up being? 71. Let me just do this in my head here real quick. Let's see, carry the 2, 71.2-ish kilograms, okay? That's his mass, cool. Ooh, but I don't want to put 55 pounds here, okay? Because that's not going to shake out to be meters per second squared. That's going to shake out to be gibberish. So I got to remember my important information about Mr. Harding here. So let's try to be a little savvier this time. I'm going to put the newtons upstairs. 1,000 newtons is to 225 pounds downstairs, as question mark newtons is to 55 pounds downstairs. 171.2? Yeah. What did you say? The ether? Whoa, that's a callback if I've ever heard one. What's the new thing?
Unconscious trash can.
That doesn't even work. Should have been like Taneem's tantrum or something. Calm down, Taneem. Everybody knows, buddy. Jeez. All right. So, all right. What do you get for newtons for 55 pounds? 21? Does that make sense? 1,000 newtons to 225 pounds. Question mark newtons to 55 pounds. Seems like the newtons should be bigger, right? What you do is take 1,000 times 55 and then divide it by 225. How much? 215. Can I believe him? 215 newtons. So I can kind of mental math this to be in the ballpark of 3 meters per second squared. Is that about right? About, right? We got roughly 21 to 7 there as a ratio. 215 to 71.2. In the ballpark of 3 meters per second squared. Now, I need you to kind of think about this a little bit. I don't know if I busted this out the other day, but relate it back to the bowling ball activity. Okay? You got a bowling ball, you got a mallet. Hold that this way, sir. Thank you. So if I start tapping this thing, right now the force is balanced. As soon as I start to tap, the force is going to be unbalanced. You might need to scatter just a smidge. The force is going to be unbalanced. How does the direction of the unbalanced force compare to the direction of motion?
Same amount.
They're going the same way, right? It's moving this way. The unbalanced force is this way. It's getting faster. What does that tell you about the sign of the velocity compared to the sign of the acceleration? Same sign. Okay. So velocity and acceleration and Fu are pointing that direction. Okay. Those three things are pointing the same way. It gets faster. All right. That's what's happening here. The unbalanced force is in the upward direction. The direction it's moving is getting faster. Okay. Here. What's up? I feel like the middle row of tables is getting close to the front. If you want to sit in the front row, just sit in the front row. Don't be like pretending. Well, I don't want to sit in the front row. Yeah. Thank you, Tani. Read the read. All right. Same verse. Different song. Well, same song. Different verse, maybe. All right. So M4. When the scale is reading 120, what is going to be going on with the free body diagram? Okay, so have a go at that on your whiteboard with your friends and your friends' friends.
Wait, so this is the free body diagram for
120-pound scale reading.
Is this right for man 2 then?
This is man 2.
Okay.
212 up, 177 down.
Yeah.
Cool.
And then, okay.
You get an FU of 55 pounds, point down.
Yeah.
No.
Okay, we got it.
So again, we just talked about man 2. Take some of those ideas over to man 4. Scale reading 120 pounds. What's the free body diagram look like?
This is man 4. And this is.
What's happening to the motion of the elevator?
So the elevator is going down.
It's going down, which means that
Yeah, so this is. Oh, so this is meant for. Okay.
So this is 1, 2, 3.
Okay.
But it's the same man.
But it's the same name. Meant for, yeah. I don't see what. But the other one. The one you didn't see.
Is that right? I must have, right? I used 2.25 pounds.
Yeah.
Pinter, which group is your?
This one.
Damn it!
It's this one.
Power School.
You did this to yourself.
Power School did this to myself.
It's increasing, right?
What? Bro. You left me hanging on 215. This should be what again? 244. So then what is this actual number here for the acceleration? 3.4-ish? All right, in the ballpark of 3 was the long story short. Now I got to move this even farther over. That's not how you circle. Wow, it took you a whole trimester to name? All right. M4. All right, friends. Camera 1, camera 2. Let's go. A is thumbs up. B is thumbs down. What do you got here? Join the party. 157 pounds up, 120 pounds down. That's a thumbs up. 120 pounds up, 157 pounds down. That's a thumbs down. Where are you at? Start rubbernecking, looking around the room. Looks like this vote is swinging towards, okay, sideways in some cases, but generally down, okay? Generally thumbs down. 120 pounds is a reading from the scale. That implies that that has to do with the interaction with the scale. So that is going to be F smoosh poosh man scale. For his weight to change, for this 157 pounds to change, what would have to happen? He'd have to eat a sandwich. He'd have to take a really big poop, okay? He'd have to change his mass, the amount of stuff that makes him up. The thing that's changing is his interaction with the floor. The floor would be more smooshed, so he's more pooshed. All right. If we add these arrows together, 120 pounds up, and then 157 pounds down. Now, again, the arrow to balance this would point up. We don't want to balance it. It's not balanced. What goes in here? What goes in here? Thank you. All right, a big stripy FU. How big is this FU? 37 pounds of FU, okay? Same drill again. His mass is based off of whatever you want to call it, his rest weight. Like he's 157 if he's just standing there. So we'd use that 157 pounds. And we know that there are 2.25 pounds for every kilogram based on the numbers Mr. Harding gave us. So that's 71.2 kilograms. So if I want the acceleration, I take the FU over the mass. I got 71.2 kilograms for the mass. The FU, 37 pounds. And again, that is roughly 1,000 newtons for every 2.25 pounds. And so this is going to shake out to be
Wow. Oh, your calculator's not working.
what'd you get? My batteries are low.
I got you. Hold on. You can do it in your head. 16,444.
Hey Alexa, what is 37 times 1,000 divided by 2.25?
The answer is approximately 16,444.4444444.
I said that.
All right, it's Samsung. It answered to Alexa. Okay.
Hey Siri.
I'm kind of feeling like this number is not correct though.
It's not.
Yeah.
Hey Siri.
Who's got real Siri?
How much is 37 pounds times 1,000 divided by 200? Oh my gosh, dang it!
That's right, Hart.
16,000? Oh, what did I do? I'm a dummy. Sorry. Thank you. I don't want 1,000 there.
Yeah, I don't know why that was there.
Let's see. What's this going to shake out to be? 1,000 newtons, not to 2.25 pounds, but 225 pounds. So I guess it'd be 10 newtons for 2.25 pounds. So it's not Google's fault. It's my fault. Hey Siri, what is 37 times 10 divided by 2.25?
The answer is approximately 164.444444.
She's got esteem issues, but it works. All right. 164 newtons. So I put that in here. It's not letting me erase. There it is. 164 newtons. Hey Bixby, what is 164 divided by 71.2?
The answer is approximately 2.303371.
2.3-ish meters per second squared. Now, the elevator is moving which direction? We got to scroll way over to get to the velocity graph. The elevator is moving which direction? Hey, that should have been a coil response and it wasn't, so you better talk to your friend, okay? Only you can prevent dumpster fires. So during section 4, the elevator is moving up or down. Run it by your neighbor real quick. Okay, the elevator has a positive velocity, so it's moving up. But the acceleration is negative, so it is slowing down. All right, so we got negative 2.3 meters per second squared. This was positive 3. Man, you guys are going to be replaced now that I know that Siri and Bixby will do my mental math for me. I don't even need you guys. Just teach this class alone. All right, so we've got the accelerations from these situations. Now, something to be mindful of here. Okay, we talked about in the previous example how the velocity and the acceleration were in the same direction. It's getting faster. That was also the same direction as the FU. What about this situation where it's moving about never? Okay, so it's moving this way. So we're joining this already in progress, but then slowing it down. How did the direction of the motion compare to the direction of the acceleration? How did the direction of the FU compare to the motion? Opposite, right? Velocity was pointing that way, acceleration was pointing that way, FU was pointing that way, okay? So the first example, velocity that way, acceleration that way, FU that way. Now it's velocity that way, acceleration that way, FU that way, okay? Seems like acceleration and FU are pointing same direction. That's an important understanding.
So the FU is the little bar.
So right now the forces are balanced, but as soon as they start to tap it, they're unbalanced. If it was rolling like this, that's like that.
They're cold.
What are you going in for? Okay, so important understandings. The acceleration is pointing the same way as the FU. Okay, so we can kind of pull that out of here. So acceleration equals FU over m. Units wise, we want to deal with meters per second squared. So we can deal with newtons per kilogram. What? I've heard that before. AKA kilogram meters per second squared per kilogram. And acceleration and FU are always in the same direction. Hey, gang, what word should you always look out for in science? Always, okay? But so far, in 2 total examples, we found that the FU and acceleration are always in the same direction. All right, 2's not a lot of times. So let's, oh man, I gotta think about clocks here. We're good, we're 20-ish minutes. So next up on the docket, AP, UBFPM. All right, hey, like, take a picture of your whiteboard if you like. Okay, make that a thing. And then here's where we're going next, provided I can figure out where I put the printouts. Ah, here we go. All right, this next thing's kind of progression.
Oh, my finger's in the picture.
Is that yours? Can you just size?
Oh my god. I need to Okay.
Take a picture of it. Keep your whiteboard though, you're gonna need it. Yeah. Take a picture of your whiteboard, but then 86 it. All right. And in the end, you're going to inadvertently get some practice with CHM on this week. So it's good because hey, tomorrow is the CAPM unit test. Okay.
What did he say?
You're keeping your whiteboard. Here's where we're going. All right. So I just handed out this worksheet. You got an 80 kilogram box. Shelves to the bottom of a 2 meter long ramp with a constant speed of 1.4 meters per second. It's a model question. Which models apply to this situation and why? And oh man, we got a lot of models now, so we're going to draw at least 4 diagrams and or graphs to illustrate the situation. Choose the diagrams and or graphs you find most useful. And then, using the models you've chosen and the graphs and diagrams you've drawn, solve for as much unknown stuff as possible. Okay? That's this situation. On the whiteboard.
Here you go.
Oh, thank you so much. Bring it right out.
Like a child, bro.
Oh.
We're not even around outside.
We're supposed to whiteboard?
It's about to be like the.
Yeah, that's the point where we're going to put it on the whiteboard.
No, I go yours. I'll go yours. I have some.
ABC? Yeah, we're doing all number 1.
I mean, I could like ask. I might ask my teacher if we're doing anything, right? I'm rolling hard. Next year, boys and girls overlap. Yeah. Why? They overlap. They overlap like week. So we're gonna go start the boys season, right? Yeah. So you remember how many people there were? Like 65 people. 65 guys. They voted to overlap them for some reason.
Wait, so does that mean that girls take us a week later, or
So girls a week later. Girls is tapering.
I'm thinking that was the BPM model.
yeah? So it has I don't know. Somebody's
Because it's going at a constant
Boys and
speed,
girls soccer state.
and the speed is the velocity. So the velocity is constant. So I think it's does that make sense?
Yeah.
But
What are the other options?
It could be CAPM, like constant acceleration, constant velocity, or it could be the balance force.
All right, what's happening? Oh, no Kramer today.
Yeah. For diagrams. So we could draw.
Taneem, where'd you go?
So we have to draw all the graphs and we take one that makes sense. We have to draw the switch, sound graph, electrical sound graph, acceleration.
Yeah, and then we have to draw one more. So we could do like a rod diagram.
you should mark it
Yeah.
out. I swear, I am the Boy Scout.
Anything Los Chavez at Los Chavez at the bottom. Okay. So but it's going
800 kilograms. So 8,000.
Hey, dirty little secret. Parents do have favorite children. Teachers do have favorite students. And you should have some favorite graphs and or diagrams here.
I am.
They're not all the same. So if you don't have a velocity versus time graph, chances are you're doing it wrong. If you don't have a free body diagram, chances are you might be doing it wrong. You got a little bit of free body.
Wait, no, I did this wrong. That's what I'm saying.
I saw this on TikTok, and
that's velocity.
cancels a big ring, and it actually works really well.
And so then it goes. So we got 1.4 meters per second times
Wait, would this one be
seconds. So it goes a total of 2 meters. And we want to find how long it took. So that would be, should be 0.7.
This would be
Yeah. So it's only 0.7 seconds. I don't know, maybe. Okay, so then This would be like that, right?
Okay.
No,
Wait, no.
No, it can't be.
It would be a line.
How are you feeling your signature?
Shouldn't it be?
Because it's starting at the top. But
Yeah, he's starting at the top and going up. He's not starting at the top. No, he's not starting at 0. He's starting
And
at
then, yeah.
Oh.
no, I think it starts here. I think it starts
he
at 2
starts there.
and goes down to 0.
He doesn't say jump.
Yeah, it says it goes to the bottom of the ramp.
So does that mean it's going down to 0?
Yeah.
Okay.
And then
So this is,
we can do a free body diagram.
What about exploration?
The slope of this is 0, so acceleration versus time graph, we can do it.
Oh.
But it would just be Does that make sense?
Yeah, it's 0.
I don't know, man. What do I feel?
oh wait.
Okay. So now we have so for the box. Okay, so there's gonna, we can do a systems here first. So we got these box.
Well, that's when. Oh wait, that's
I don't know.
It's just the box.
All right, you got about another minute to figure out some unknown things on there, and then your board's need to go up front for good or ill, even if you don't think you're all the way done.
Friction.
So basically, like this is providing. I had friction.
Oh wait, we could do
Is that an incline? Friction would be going this way.
Oh yeah, this is on
And swoosh would be going 90 degrees.
Yeah.
Wait, this is 20.
No, it sounds like 0.
This way? I don't know.
Yeah, it's supposed to be. So we don't know the friction.
Yeah.
We know how to find that. We don't know the
I was born on January 7th.
We know, but we know, which is 400.
Yeah, I think.
Wait, seriously, are you down? Because I'm getting a lucky tattoo when I turn 18.
Like on cheek?
No, but I'm thinking like, Leah said under the arm. Don't be a little baby.
Oh, wait a second.
Swears.
This one thing.
Wait.
Okay, this is the. Yeah, because the musical. It's like, we know it's-
All right, run what you brung. Bring your board up front, even if you're not done, let's see what you got.
Okay.
Something's done, window of time.
Hey James, go put this up in front.
Whiteboard.
Yep.
You're just a diagram.
You're gonna say your English things.
Okay.
Chest
all the way out. All the way. Yeah, we got it. Big chest. Look confident. Look confident.
All right, we are last in. So flip one of those boards.
I want to put your own board. Put your own board.
Put your own board. You won't. You won't.
Oh, you're right. I won't.
All right, let's hear from Mulan.
Thank goodness.
All right, everybody sing a song from Mulan while they make their way up front.
Let's get down to business. To the beat. Stop on. Yeah.
All right, Mulan. Everybody has a theater. That's exciting. Hey, shush. Which model's applying why?
So it says it's moving at a constant speed of 1.4 meters per second.
Yep.
So that means it's a constant velocity.
Okay.
And since it's constant velocity, that means the forces are balanced.
Okay.
And constant velocity means acceleration is 0. So constant acceleration also applies.
Okay.
Yeah, move on.
All right. Cool. Somebody else talks about some of the grass indoor diagrams up there.
So we did a system uniform position versus time, velocity versus time, and acceleration. Acceleration 0, they gave us some velocity, and this is like going down the ramp. And then
Did you figure out any additional information based on what you were given? I see a time of 1.43 up there. What's that all about?
Yeah, so the ramp was 2 meters, and the car's going, the box is going 1.4 meters per second. So we did 2 divided by 1.4, got us 1.43. So it went the ramp in 1.43 seconds.
Fantastic. And then they also found the acceleration, which was
0.
0. Okay. Hey, did you catch the part where all 3 people talked about stuff and it kind of seems like they knew what they were talking about because they talked about it in their group?
Yeah.
We should do that more often when we're whiteboarding. That was really done, Mulan. Thank you. All right. Go ahead and store these boards in between these legs. All right.
You know,
Because your name's Nate Dog. That's where I got it. I don't know what we're even. It's just like a thing that person is somewhere more. Yeah, I just don't get like what up, man. We can't really tell. Like we're not supposed to tell the story, but like I don't know. Are we
Polio
just
check?
connecting it? Oh, no, I'm into the thing. The whole story.
Please make sure your markers and socks go back. Please make sure you push in your chairs. Good things to review for tomorrow. CAPM 1, CAPM 2, the CAPM extra practice problems that are on Canvas for you. If you've got particular topics you'd like to see screencasted, then email me with that. Tomorrow is the CAPM unit test. There are also the CAPM, whatchamacallits, essential understandings listed on Canvas. That's the stuff you should be good at prior to the test. This I did, yeah. That's all I got. Yeah. We got questions. Sorry about the thing we just did. Yeah, the test tomorrow will not have this.
I just like this.
Yeah. So what is this?
said it was easy.
I didn't feel great afterwards.
You said it was easy.